Good morning, everyone. So this summer I worked at CU Boulder's Thermochronology lab, analyzing the exhumation history of the South Park Basin in Colorado, the Colorado Rockies. So I'm going to start off with my question at the beginning of the summer. Why the Rocky Mountains? What is so interesting about them that there's been so much research done there? So for the Rockies, they are a mountain range that didn't just uplift one time and we have what we have now. The first Rocky Mountains were called the Ancient Rockies and were uplifted over 500 million years ago. Those were eroded away, and then the second set of mountains came up about 300 million years ago. Those were called the Ancestral Rockies. Those were also eroded away, and then about 75 million years ago, we had the Laramide orogeny that uplifted the modern Rockies that we have today. The modern Rockies in themselves are extremely complicated. They have a complex history, and the crustal root underneath the mountain does not justify the elevation they are at now. There's a lot of debate around the topic, a lot of studies being done to understand what's happening with them. My project, the purpose of my project was to add definition to this history. We're going to add data. We can't solve the mystery in one summer, but we're adding data to help with the progression of science in the subject. So for a quick history of the Rockies, for orientation, down at the bottom you have 4.6 billion years ago. That's the beginning of the Earth. At the top you have the present time. I just mentioned the Laramide orogeny between 75 and 45 million years ago. That's the box right there. And then we have the Rocky Mountain erosion surface. So as the mountains were being uplifted, they were being eroded at the same time. And so by the end of the orogeny, around 45 million years ago, there was almost no topography. The topography was fairly flat, and so at 45 million years ago, we had fairly flat topography in the area. Following that, we have the Ignimbrite flare-up, which was a massive volcanic event that continued from 40 million years ago to about 25 million years ago. And then the Rio Grande Rift started opening up around 28 million years ago, and that separated the Great Plains from the Colorado Plateau. After that, we had a period of deposition and then a period of erosion that is ongoing today. So for my study area, as I said, I was studying the South Park Basin, and for orientation, this is Denver. We have Colorado Springs, Aspen, and this is the South Park Basin that we were studying. On the right side, you have the Front Range. The left side, you have the Swatch Range. And for my sampling method, so of all the basins, why did we select the specific samples that we selected? For that, I'm going to talk about the Wall Mountain Tuff. So the Wall Mountain Tuff was a ash flow that was the result of a massive volcanic eruption during the Ignimbrite flare-up. So we just talked about the Ignimbrite flare-up that occurred between 40 and 25 million years ago. So when exactly was the Wall Mountain Tuff erupted? That is 36.7 million years ago. Right around this point, there was this eruption. The Wall Mountain Tuff flowed across the South Park Basin. So this is an image from one of the sites we sampled. The basement granite was what we were there to sample. And if you can see right on top of it is the Wall Mountain Tuff. And this stratigraphic relationship was a key point to every place we sampled. We have the basement granite, and right on top of it, stratigraphically, is the Wall Mountain Tuff. This is another site we worked at. We have, again, the basement granite, and in the distance you see that directly above that is the Wall Mountain Tuff. So why is this important? Well, we're doing dating on these samples, and having a date of 36.7 million years gives us an upper dating constraint. So we know that these samples were at the surface at 36.7 million years, and they cannot be any younger than that. They couldn't have been exhumed after that. At exactly 36.7 million years, these samples were on the surface. And so if we go back to this map, I'm going to talk about my samples. And you can see 5 stars on here. 3 yellow ones are the samples that we dated. The 2 blue ones are the ones we have but have not yet dated. So for ease of reference, I'm going to just refer to them as the west sample, middle sample, and the east sample. And then we're going to talk about the dating method, the thermochronology part. So what is thermochronology? Most minerals have uranium and thorium elements in them. And as these elements radioactively decay, they produce helium. And at higher temperatures, the crystal lattice is not solid enough to keep the helium within the mineral, and the helium escapes. As the rock cools down, the crystal lattice solidifies, and the helium is all maintained within the lattice. So that's for the thermochronology part. Now, apatites. Why are we using apatite specifically if these elements are common? So to explain what apatite is, it's a common phosphate mineral. And from what you can see in the picture, this is a much larger sample than when we would normally use to analyze. But it looks the same. It has 6 sides. It ends in 2 pyramidal. You have 2 pyramidal terminating ends. And we use it for low temperature thermochronology, and that is because apatite it starts retaining helium at about 65 degrees Celsius. So when the rock reaches 65 degrees, the crystal lattice is solid enough to keep the helium in the mineral. And that's a proxy for the upper 1 to 3 kilometers of the surface. So if we have an apatite and we have helium in that apatite, we know that it was within 3 kilometers of the surface. And now for the mineral separation. So on the left side, you have a picture of the mineral at the site, collection site. On the right side is what is left after the processing. So first we have, again, the collection site. The next part is the rock crushing. We process the mineral so that all the grains are smaller than 500 microns in size. And then we separate them to reduce the volume using water, the Wolfley water table. We have the apatite is a denser grain, so that allows us to separate that. It is also non-magnetic, so we use magnetic separation to remove all the magnetic material. And then we put it through density separation, again, using heavy liquids. So like I said, the apatite is a denser mineral, along with a few other minerals that will sink to the bottom, and that gives us this final product. So we take this final product, and we use a petrographic microscope for grain selection. And what we're looking for is, we have 3 criteria in apatites. First, we have inclusions. We have to avoid inclusions. And if you'll see the picture where the arrow is pointing, that is an inclusion, and this is what we want to avoid. And what an inclusion is the precipitation of a different mineral within the apatite. And that will throw off our date. It has either different uranium thorium content, or due to other variables, it will give us an incorrect date. And so we absolutely must avoid these inclusions. The next thing is that it has to be large enough for us to reduce the error margin in our dates. We try to find the larger apatites. And if possible, we look for euhedral shapes in apatites. And what that means is that we can see clear crystal faces. Typically, an apatite would have 6 crystal faces. That's one. In this particular sample, you can see the lines between the faces, and if we can find 2 pyramidal terminating ends, that's the best option. And what that does for us is it makes it easier for us to calculate the surface area of the apatite. So now for the results of my sample, for dating my samples. So first we have the first sample, on the west side, we had laramide age exhumation between 70 to 59 million years ago, and what that means is that during the laramide orogeny, this sample was uplifted to within 3 kilometers of the surface. Before that, would have been deeper. And then the middle sample is significantly different in that it was much older. And if you'll notice the distance, it's about 20 kilometers between them, but the age difference was massive. So for this one, it's definitely pre-laramide. The dates go between 345 to 135 million years ago, possibly early Mesozoic exhumation. And what that means, again, that by the laramide, this sample had been on the surface, within 3 kilometers of the surface, much longer, long before the beginning of the laramide orogeny. And now for the last sample, that gave us an in-between date. So it was already at the surface at the beginning of the laramide, possibly exhumed in the late Mesozoic, about 173 to 108 million years ago. Now what this graph shows, so we use the software called HeFTy to model the thermal history of these samples. And what you're seeing here is on the x-axis, we have time in millions of years. On the y-axis, we have temperatures in degrees Celsius. The pink lines are good fit paths. The green is the acceptable fit, and the blue is just a mean of all the lines on there. And so up here, we have the wall mountain tuff constraint. And what this does for us, like I said, it provides us with an exact placement for the sample at 36.7 million years. And what the software does is it forces all the lines to pass through that box as it's modeling. So whatever modeling path it takes, it has to go through that box. This here is the laramide orogeny. And you can think of temperature in this case as a proxy for depth. So the further back we go in time, with less data we have, and it's a lower resolution, we have more possibilities for the history of the sample. But regardless of that, you can see that it was not retaining helium at the beginning of the orogeny. And as the orogeny progresses, the apatite is getting cooler. And by the end of it, it is fully retaining helium at about 45 degrees. So this is the middle sample that I already mentioned was much older, had been exhumed to the surface much sooner than the west sample. This is the wall mountain tuff constraint. Here we have the laramide orogeny, and if you look to the left side, you can see at the beginning that the depth of the sample was about 65 degrees. It was about 65 degrees, so it was already retaining helium a bit before the orogeny started, and it progresses again, but at there's a less dramatic difference in temperature. For the third sample, the wall mountain tuff constraint again, the sample is again starts off deeper because it is a younger sample. It was exhumed later than the middle sample, and it starts off at about between 80 to 70 degrees and cools off as, and by the end of the orogeny, it is cool enough to fully retain helium. So possible for the biggest conclusion we have from this is that exhumation was definitely not uniform across the basin. There was a variation in exhumation and erosion rates from the west sample to the east sample. Even though the difference was not great, the exhumation rate was very different. Now, possibilities for that is that there could have been a variation in burial depth across the basin. So the west sample could have been buried deeper and partially reset the dates, whereas the middle sample was unburied. There's another possibility that the west sample could have been uplifted at some point, or there could have been a difference in the uplift across the basin, so the west side would have been uplifted faster and cooled off. So for future work, we're going to date the last two samples. We're going to date zircons from the west sample to give us higher resolution data further back in time and for higher temperatures. And there's a possibility of doing further sampling along the basin. And I would like to thank the NSF for sponsoring this project, UNAVCO, CU Boulder, and everybody else who made this possible, my mentors. And I can take any questions now.
Okay, any questions for Fatima? Oh, Chris, sorry, I didn't see your hand.
Your map showed a number of faults in the area. Are those all laramide age faults, or is there anything else that might have affected your samples?
The majority of those faults were from the Rio Grande rifting, so they would have been after the laramide and wouldn't have affected the ages of my sample.